In this Chemokinetics podcast on thermodynamics, heat, work, and the first law of thermodynamics will be discussed. A major thrust of combustion is the generation of heat and how to utilize that heat. Therefore, an important topic within combustion is the thermodynamics, which quantifies all aspects of work and heat release that occurs during the combustion process. An example is the complete combustion of methane. We all know that heat is generated because of the reaction of methane and oxygen. Why does this reaction generate heat? Where does the heat come from? Thermodynamics quantitatively answers these questions. The first law of thermodynamics basically says that in going from one state to another, all energy has to be accounted for, the conservation of energy principle. Delta U is the change of energy of a system after the entire process, in other words, the difference between two states. Delta Q keeps track of all the heat release, for example, during the combustion of methane and air, and heat loss, for example, by absorption of heat by the walls of a container. Delta W is the work done on the outside world by the process, for example, moving a piston. It is minus because the energy is taken out. In combustion, a system is, for example, the combustion of propane and air and the associated heat release. If the combustion process is within a piston, for example, then some of the heat energy of the process is lost in moving the piston. Thermodynamics is an extremely powerful and general field and describes many more situations than is needed than in combustion chemistry. For this reason, we can simplify possible sources of heat and types of work, tuned especially to what is relevant to the special cases within combustion. Heat Q can be generated by the making and breaking of bonds within a chemical reaction. Within combustion mechanism, each reaction has an associated amount of heat of energy generated or used due to the making and breaking of bonds. Heat can also be generated or transferred by heat thermal conduction. For zero-dimensional calculations, this is the external sink, for example, a wall of a vessel at a constant temperature. The work is restricted to mechanical PV work, the expansion and contraction of gases, the increases and decreases in pressure. A typical case is a piston. In constant volume, no PV work can be done, so the change in energy between one state and the second state is the change of internal energy. Now consider the reaction going between species A and species B. Each species has an inherent energy associated with it, its atoms, bonds, etc. Under constant volume, the energy changes due to the reaction is QV. That is the same as the energy change in internal energy, delta U. No new variable is needed. Note that we do not have to know exactly how the molecular transformations, for example the transition states that occur in going from A to B, we just have to look at the beginning and end states. Often we have no direct information how to get from molecule A to molecule B. It would be impossible, or at least impractical, to tabulate all the possible combinations of reactions. However, if we define a standard intermediate state of molecules, then we only need to tabulate the path in and out of this standard state. We just calculate the energy of the path to the standard state from the reactants, and the energy path from the standard state to the products. Although this is not the path that nature takes in going from A to B, it can be used to calculate the energy changes involved. One of the most useful aspects of the first law of thermodynamics is that it is a formulation that deals only with the initial state of the process and the final state of the process. It does not care how one gets there. Just look at the initial and final states. Each individual path, with a different combination of changes in Q and W, gives the same total energy change, as long as the initial and final states are the same. Another way of saying this is that the process is reversible. no energy is lost. The total energy can be accounted for. Reversible is another way of saying anything you can do to the system you can undo. No matter how you get from A to Z, no matter what path or intermediates you encounter, the total energy is always the same. What this means computationally is that we can use the simplest computational path. Maybe we don't know how to have all the information to calculate the energy difference between A and Z, but if we know how to get from A to B and then from B to Z, then, using the first law of thermodynamics, we can compute the energy change from A to Z. The first law says that it does not even matter whether this corresponds to an actual path taken by the system. The answer will be the same.